So this question has two parts, and we're going to do part one, which is on solar radiation and the greenhouse effect. So they give us this data, and they ask us to state the Stefan-Boltzmann law for a black body. So I already did this here, and I'm just going to read it out loud. So it is the power per energy per second emitted, which is proportional to the surface area, and also proportional to the fourth power of absolute temperature. And that's the Stefan-Boltzmann law stated right there. So P equals emissivity times the Stefan-Boltzmann constant times surface area times temperature to the fourth. And the temperature is going to be in Kelvin. So deduce that the solar power incident per unit area at a distance d from the sun is given by that equation. So what you're going to do here is you know that the sun is the shape of a sphere. So you're going to plug that in for the surface area part. So here what you're going to do is plug that in on the bottom. So it'll be, or plug that in, so it'll be 0 r squared t to the fourth. And you're going to get over d squared times the surface area, which is going to be 4 pi d squared. So that's going to equal 4 pi times the Stefan-Boltzmann constant times r squared times t to the fourth, which is going to be the solar power incident per unit area at that distance. Then we're going to use the equation we used before and plug in. So we're going to have Stefan-Boltzmann constant r squared t to the fourth over d squared, which equals, now we're going to use the data that they give us in the beginning. So I would just really quickly pause the video and write all these down so you can put them in the problem and do the problem. So let me give you a second to do that. So then write all these down, and you're going to plug those values in based on the problem set. So you're going to get 5.7 times 10 to the negative 8th times 7 times 10 to the 8th squared times 5.8 times 10 to the third to the fourth power over 1.5 times 10 to the 11th squared. That is going to give you your answer, which is going to be 1.4 times 10 to the third watts per meter squared. Then next, state two reasons why the solar power incident per unit area at a point on the surface of the Earth is likely to be different from your answer in D. So there are multiple reasons. So there's only some energy reflected. Some energy is going to be absorbed by the atmosphere. It depends on time of day and year. Weather plays a role, and the Earth/Sun distance also varies. So, yeah, that is going to be the problem on black body, solar radiation, I guess, not black body, and greenhouse effect. So,